few different ways to think of vector data that these words still get used in the literature today. Spaghetti models are just like it sounds. It's just a bunch of objects. It has no topology. There's no way to fix or test the topology, and it's just a mess to use. Um, However, it may be appropriate for whatever you're doing if you don't need topological relationships. So what is topology really good for? If you have a well-done topological data set, you can use it to accurately describe um, where things are in space. You can actually use it to model flow of things. So, for example, a stream network, topologically correct, can be used to model the flow of water from the headlands of the streams down to wherever the terminus of the river system is. If it ends in a lake, if it ends in an ocean, something like that. Topologically correct stream networks can be used to measure and calculate flow. Topologically correct street networks can be used to generate paths through the landscape. So one of the classic problems in transportation and economic geography is the traveling salesman. How do you get the traveling salesman or the delivery driver to all of his or her stops in a community as efficiently as possible? So this is something that's built into Google Maps these days. If you do driving directions and say call for driving directions between Moscow and Seattle, and it'll generate probably several paths now. These days, I think it generates three major paths that you can take to and from Moscow and Seattle. And the reason it can do that is because the street network inside Google Maps is topologically correct, and it's filled with the street network as it exists. It's filled with the speed limits per line segment on the roadway, so it knows the maximum driving speed that you should be going. You may or may not do that, but it'll know that information, and it'll be able to calculate driving time along those different paths, or approximate driving time along those different pathways. So topologically correct information is what we prefer to use. In this class, we're not going to do a whole lot with the network data model. That's something that gets covered in more sophisticated and more advanced classes. But anyway, we want to make things as topologically correct as possible no matter what. So we prefer that rather than just a spaghetti mess of things. So the way to do that, you will learn later in the class proper techniques for digitizing point, locations, linear features, and polygon features in vector data sets. So we can revisit map scale again because we need to. It's really important. So it's the ratio of the distance on the map to the distance on the ground, or the distance on the earth. Again, as I mentioned before, it's dimensionless. Doesn't matter what it is. If you have a scale, you just use the unit, and you take a measurement on the map, and you use a multiplication technique to figure out how much space that measurement actually is on the Earth's surface. So using the example in the box, with a scale of 1 to 100,000, you measure a distance of 2.5 centimeters. You want to know how many centimeters does that represent in real life. Run that calculation. X equals 250,000 centimeters, or 2.5 kilometers. And that's how map scale works. That's what it does. So here, an example of this would be, again, solve for X. Using a map with a scale of 1 to 20,000. You're doing a 10K run. On the map, that should be how many centimeters? So a 50 centimeter, kind of going in reverse. Knowing a specific distance you want to travel, how much space does that take on the map, rather than taking a measurement on the map and calculating the real world space. So it just reverses that in the equation, and you can solve for that as well. So I talked about this a little bit before, map scale, small scale maps, large scale maps. A small scale map, the small and large refer to the size of the fraction. A small scale map is a small fraction, in this case 1 to 50 million, shows a large area. It doesn't show a lot of detail about that area. Move down to the 1 to 5,000. So that's a large scale map. It's large because the fraction is larger. It's closer to 1 to 1. It shows a smaller area, but it shows a lot more detail about that area. So map scales, a small scale map, you hear something about the continental level or global scale, continental scale, global scale, small scale map. If you talk about local or landscape level things, you're talking larger scale maps. So here's kind of an interesting conundrum about the realities of using maps to show things and to try to show them accurately as to what size they are by the size of the symbol on the map. So in printing, 1 inch on a piece of paper is the equivalent of 72 points. Okay. So if we draw a line that's 3 points on a 1 to 100,000 scale map, we want to know, well, how much distance is that showing us in real space? What is that object that we just drew, the 3-point size on that map? What are we saying that is? And in this case, what we wind up with is we're saying the street is 350 feet wide, 347 feet wide. 3 points on the map equals 347 feet at 1 to 100,000 scale. So essentially, although we think that our vector data, what we're seeing on the map, is very accurate, and underneath it all, it is, but in order for us to see the street on a map at 1 to 100,000 scale, we have to exaggerate the size of the line symbol in order to be able to see the darn thing. Okay? So it's kind of a little bit of inaccuracy built into the utility of us actually being able to use it visually. For those of you who might be interested in things like this, there's a great book called How to Lie with Maps. And it points out things like this. You know, here's a reality where we literally have to exaggerate. We have to lie about the size of the road on the map in order to see it, just cartographically. You know, it's not in. You know, we have to intentionally do that in order to see the thing, but the road isn't actually that size in real life, and so it's a trade-off that we have to use in cartographic representation of the Earth's surface. And again, I'd recommend that book to anyone that's interested in cartography, in map making. How to Lie with Maps is a very good book about just pointing out some of the realities that we have to face as cartographers. We will experience and see some of the other ones later on in the class. And if you go on to take a cartography class, you'll get a lot more detail about how we construct maps and the trade-offs that we have to make in a lot of different categories of and attributes of maps in order to make them usable. So when we look at different maps drawn at different scales and think about features on them done in vector format, we can consider, for example, a 1-point line being equivalent of about 0.001 feet. So if we take map scale, divide by 1,000, that'll give us the approximate precision in feet for a 1-point thick line on a map drawn at that scale. So a 1 to 5,000 large scale map, a 1-point line representing something on the Earth's surface is 5 feet. On a 1 to 24,000 map, 24 feet. 1 to 100,000 map, that same point one, that 1 point line on the map now represents 100 feet. And on a 1 to 1 million map, that 1 point line physically represents 1,000 feet. So the smaller the scale of the map, the less precision that we have in knowing where that point line actually is representing something on the Earth's surface. So at 1 to 5,000 scale, the 1 point line is describing something at 5 feet across. That's pretty precise for a roadway, for a stream, or something like that. At 1 to 1 million scale, if it's 1,000 feet, well, the river or the road could be anywhere within that line at 1,000 feet. We're really losing a lot of precision about where things are located when we're dealing with smaller scale maps. And so that's one thing that I would ask you to remember and think about all the way through the course, is that a large scale map is going to be more accurate, it's going to be more precise in general than a smaller scale map. Or if you think of it in terms of local, regional, and global scale, maps done at the local scale are going to be more accurate. Things done at the regional level are going to incorporate some more error. Things done at the global level are going to incorporate a lot more error in them, positionally in the vector data model, if they're done at those scales, if they're generated at those scales. One of the things we can draw from this slide here, and something that you'll be experiencing through the exercises, is that each of the data sets that you encounter, vector or raster, is going to have a scale that it was generated at, its intrinsic scale that it got from its source information. And we can zoom in and zoom out. And on some kinds of information, some kinds of data sets, we're going to be able to zoom in and see a lot more detail, and like vector data, we'll be able to zoom in quite some ways and get really accurate and precise descriptions of where things are on the Earth's surface. With some forms of raster data, it's not going to work out so well. If you zoom in on a digital raster graphic, it's just going to become blurrier and blurrier like it is here. We're going to go from something that's fairly clear, we start introducing some blur in the middle, get a lot blurry on the far right, and that's zooming in, making larger and larger scale on that graphic, when that graphic wasn't really designed to be displayed at that scale. Okay, so zooming in, zooming out, something we're going to have to do quite often to examine things. Sometimes it'll be useful, sometimes it won't be incredibly useful. So the scale at which something was generated can have quite a large impact on how well it's describing things on the topology. So we're seeing here two different map scales shown simultaneously in the same area on the east coast of the U.S. So the pink data in the back with the lighter colored lines or lighter colored polygons, that has an original scale of 1 to 5 million. Okay, so that is, well, there we go. The darker one has an original scale of 1 to 25 million. So in this case, 1 to 5 million is larger scale, 1 to 25 million is smaller scale, and we can see quite readily, the differences in topology here and the ability of the larger scale data to better match the physical reality of the landscape that it's trying to depict. The smaller scale data 1 to 25 million is not doing a very good job. And remember that idea of precision from the previous slides. It can't. It just can't do a good job. It's going to have to generalize and simplify even more because it is a smaller scale map. It's as if you were orbiting the planet in space and trying to trace the outlines. You're not going to get as much detail as if you're flying overhead in an airplane or if you're flying overhead in a balloon. And how that plays out when we're actually digitizing things is that in this case, on this slide, we're having a display scale for both of those insets, both approximately 1 to 500,000 display scale, and using the 1.5 million and 1 to 25 million original scales for the data. The one on the left with all the little blocks is 1 to 5 million. And so you can see the little blocks are they're little nodes that we're doing and incorporating when we click on the map or we click on the image that we're digitizing from, tracing the outline. We're able to get a lot more detail, a lot more of those tracings done accurately at 1 to 5 million, whereas if we're zoomed back out to 1 to 25, we're going to get a more simplified version, a more generalized version of the coastline, which is fairly complex. Now, if we were doing this, tracing the outline of the continent or the shoreline at 1 to 24,000 scale, we get an incredibly complex description of that coastline. It would be very accurate, much more accurate than either of these two that are done at much smaller scales. Okay. So that's the main thing I'd like to point out about this. Price, the textbook author likes to mention something about resolution and storage space, and it slows drawing. And well, that's true. So if you generate a map at 1 to 24,000 scale, but all your work is being done at the continental level, where 1 to 5 million works well, then there's no reason really to be using the 1 to 24,000 scale data. And you might consider trying to find something done at the scale that you're interested in, 1 to 5 million, and use that instead. That's kind of a personal decision these days. Again, given the speed of computers and the amount of RAM that we have access to, and hard drive capacity, it's not as much of a problem as it had been in the past. Even when this particular workbook was first published years and years ago, it was much more of a problem. So how do we find out what the scale is? We might want to know that. It's documented in something that we call metadata. Metadata is information about information. And that may be published on the web if you get your information, your data set from a website. You might find it there, printed, and you can just save a copy of it. You can also inspect your data set using ARC Catalog and look at the metadata there, and it'll tell you, hopefully, if someone did a good job when they created it, it'll tell you what scale it was generated at, and some ideas about accuracy and precision in the production of that data set. Hopefully you'll have some idea about that, so you'll be able to know if I'm using something that was generated at the 1 to 5 million scale. I know that's not very good if I'm doing landscape level work, that everything else that I'm using is a 1 to 24,000 scale. And I probably shouldn't be using the 1 to 5 million for that. It's just, it was done at such a much smaller and less accurate level of detail. It's not going to be very useful for my project that needs higher resolution, larger scale data. And so that's one of the things that why we really worry about scale in general, why we're spending some time talking about it here in the class.